Welcome back, everybody. So we are going to continue on data frames. I have the feeling pre-partitions are not entirely clear. So maybe I'll come back on this. I have a few more examples in the data frames, but I had the feeling it didn't exactly completely got across. So I'll keep that in mind. But don't worry. So now let's move to repartitioning. So pre-partitioning is an advanced feature. That's for advanced users who really want to control the data flow. Let's put it in parentheses for now and go to data frames. So data frames. You probably remember data frames from the data modeling and validation lecture, where we use data frames for valid JSON. Remember, when you have a collection of JSON documents and they're all valid against a specific schema, we can actually save them as a Parquet file based on the columns, right? And that's basically a data frame friendly file. So we already saw that data frames are very good at reducing the file size on disk. And because of the columnar storage, they are very good for push downs to be able to just read what you need, which gave birth to the Dremel framework. All right, but actually data frames are much more than that. And in fact, they are so much more than that that also Spark has special treatment for data frames. They didn't exist in the early Spark versions. That was added a little bit later. So the idea is that we have these RDDs here that are mapped by transformations, and we can write codes like this that builds your DAG implicitly with computing an RDD from another RDD. And then that gets you a DAG of RDDs, right? So here, map, filter, map, these are all narrow dependencies. That's a single stage, do you agree? Right? Map, filter, map, single stage. And then count by key is the action that gets a dict that gives you the results. Now, this is a JSON data set, and Spark RDDs do not understand JSON. JSON is just whatever. It's a format it doesn't understand. So when you read that file, it's just text. It's going to be lines of text that so happen to be serialized JSON, but the user needs to take care of it themselves. So the user has to explicitly maybe do import JSON in Python and JSON loads. Whoever has already used JSON loads in Python, right? So you know that, right? So that's a Python library, and you have to load it, then you get dicts, right? If you parse an object, you get a dict in Python. And so now you map it to dict, so you have an RDD of dicts, and then you need to use Python syntax to look up the dicts or do things. But you see, that code is not very easy to read, right? The way you can tell is that it's basically some salad of parentheses and square brackets, right? So when you start writing code that ends up with a salad of parentheses and square brackets, then this is basically when it hits the limits of writing Python and using APIs, right? And so people realize that requires a lot. You need to know the RDD transformation API. You need to know JSON. So that's a lot for the user. And so this is why the Spark team had a brilliant idea. They decided to create a new technology in addition to RDDs, a new generation of RDDs. An RDD could basically be anything, right? You can have RDDs of integers, RDDs of strings, RDDs of pretty much anything you want. They can even be polymorphic, right? You can have RDDs of some class that has different subclasses. So you can have basically heterogeneous RDDs. What if we had an RDD of rows, as in the rows of a table? So I have an RDD of rows. Do you agree that if every value in my RDD is a row, and the rows have the same schema, so these are all rows of the same table, who agrees the entire RDD is basically a table? Right? Because an RDD is a collection of rows. So basically the idea is to have these special kinds of RDDs that are RDDs of rows and that model tables. Not only tables, data frames in general. So you can have nestedness and so on. And so this is how data frames made their way into Spark, right? So they were in Pandas and so on at many other places, but now they are made their way to Spark. And so Spark was extended to have data frames, data frame transformations, just like you have the RDD transformations, you have data frame transformations, and so on. Why is it important? Well, it's important for exactly the same reason why we wanted to store our data as Parquet. because it takes less space. So data frames are stored in columns. In Parquet, it's organized column by column. When it's the same in Spark, it's also going to be organized column by column locally on the machines in memory, right? So the memory layout is optimized. For example, when you have a collection of JSON documents that all have the same schema, you don't need to repeat the keys. If the keys are always the same for every document, then you save space in memory. For whom is that clear? Right? So the same optimization we did on disk with Parquet, now we do it in memory with data frames in Spark. So what it means concretely is the size, the footprint in memory diminishes if you use a data frame instead of an RDD of disks, for example. But there is something even better than that. It is that since we have RDDs that are data frames, we have a language to query them, and that's SQL. So now you see the SQL brush-up that you did at the very beginning was very useful because, of course, it's good for PostgreSQL. It turns out that you can also use SQL in Spark. You can use SQL to query data frames. So it can look a little bit like this. So here you directly read JSON. So now you see it's aware of the JSON format. You can also read Parquet and others. Then you give it a name. Let's call it data set. And then you just say Spark SQL. Select where order by, that's basically SQL, right? And you just select from the data set that you've just given a name right there. Who is with me? Right? So it's awesome because now, instead of having to deal with the salad of parentheses and square brackets, you can simply write your SQL query in there and directly execute a SQL query against your data frame. So now I'm going to show that a little bit to you and show you also the limits of this. But this is the idea. So the idea now is that we can open many different formats and Spark will figure out the schema. For example, imagine you have a CSV file like this, dataset.csv. Spark can create a data frame out of it, not surprisingly with 2 columns, and it can infer the types. That was the question you asked earlier, right? When Spark can scan the data to understand. So here it needs to scan. There's also optimizations where it only samples the data. So it's not reading the entire data set, it just reads a little bit of it, and based on that sample, it assumes the schema is going to look like this, right? So in that case, it infers that foo is an integer and bar is a Boolean, and then you can directly load it into memory as a data frame. And just like RDDs, the data frame is partitioned and spread over machines and so on in exactly the same way, okay? CSV, JSON also, so it's also able to read a JSON file like this, right? You see that foo is an integer, bar is a Boolean. It's automatically inferring the schema, right? So you don't even need to, you can, of course, if you want to specify a schema, you can, but you don't need to. Spark will infer the schema for you, right? Who is still with me? Right? It makes sense, right, to load this document as a data frame, right? That should be intuitive. So there's plenty of formats like this that you can load into data frames. Now, there are people who love salads of parentheses and square brackets. And so instead of SQL, they prefer to write their own transformations, especially if you love pandas or you love, writing API code, then that's for you. And instead of SQL, you can use data frame transformations, filter, sort by, select. There's plenty of them. Be careful, it's a different list. There's the list of RDD transformations. There is a separate list of data frame transformations, not the same API, right? They look a little bit alike, but they are not the same. So you have two ways of manipulating data frames. Either you love APIs and you use the transformation API, data frame, transformation API, or you love SQL and you write directly SQL in order to query the data frame. Just to get a feeling, who would prefer to use the data frame API? Okay, who would prefer to use SQL? Right? So you see, there's something for everybody, right? According to your preference. So typically, the people who love to use the data frame APIs will often be engineers that basically implement something more complex. For example, RumbleDB, I will explain what it is a bit later, but when we implement it, we use a lot of the API calls because it allows us to play more like a Lego game, right? The end users, maybe also not from computer science, will prefer SQL typically. But as an end user, even as a computer scientist, I would probably prefer SQL for my productivity because it's so much direct to write. Okay. All right. Now, very good news for you. There's a type system for Spark data frames, but we've covered that. I showed you the very generic type systems that there's for many technologies. So if I show you the available types, that shouldn't surprise you, right? Numbers, Booleans, binary, timestamp, date. There is absolutely no surprise in there. We've done that a couple of weeks ago. They might have different names, right? But this is the idea, right? So I have here another correspondence list where you have the data frames type. So that's the types that the columns can have in your data frame. That would be the corresponding Java types, the corresponding Python types, the corresponding JSONic types, right? So this is the correspondence table, right? Who is not surprised by the type list? Right? We've covered it a few weeks ago, right? So I don't need to say much. And we have array type, map type, struct type. So I told you that some have a map type that can map keys to values of the same type. So there's technologies like that. My preferred types here in terms of database person is array type or struct type, because typically that's an array and that's an object, right? So the rows will have a struct type and will be JSONic objects. The arrays will be arrays. But for those who want to map keys of a specific type to values of a specific type can also use the map type if they want. Okay, so we have this type system that doesn't have any surprises. In terms of formats, it's very modular too. You can read JSON, you can read Parquet, you can read CSV, you can read text. Then it's just a data frame with one column with just the string, the lines in there. You can read with JDBC. JDBC is the technology that connects to a relational database, right? So it's a way to connect there, and you can get a data frame from a relational database, from PostgreSQL or from whatever a database you want, any relational database system. Plus, for more formats that are not built in the API, you have this format where you can have all kinds of plugins with many more formats to pick from, like Avro was one that I mentioned, right. By the way, here I put HDFS, but of course it could be S3, it could be Azure Blob Storage, it could be file for your local file system, right? It's fully generic. Who is with me? Right, so that's just a restaurant menu. These are all the formats you can have. These are all the types you can have for data frames, right? So then you just pick according to what you need. So now, if you decide to read a file into a data frame and to manipulate the data frames with Spark SQL or with the data frame transformation API, what's going to happen is that Spark will compile what you want to do from your query in Spark SQL or data frame transformations to a physical query on RDDs. It means that behind the scenes, there will be some very physical RDDs that implement the whole thing. So there's the logical plan on the data frames that is compiled internally to a physical plan. Right? And so we have, that's a picture from the paper, we have this cascade of optimizations that are done on the data frames to basically figure out how to execute it as fast as possible and as efficiently as possible. So this is called catalysts, the code name of that. It's basically some very complex and very carefully architected system that basically takes a data frame and a SQL query, and then all the way to RDDs and RDDs transformations. That is the power of data independence, right? Logically, you have data frames. Physically, you have RDDs, right? And you compile from the data frames to the RDDs. Who is with me? Okay, just checking. Now, SQL looks pretty much the same, and they even improved it because not all the functionality was available at first. Like, for example, I think offset wasn't available a couple of years ago, and they very recently added it in the language support. So you see, they keep adding features. But here too, you shouldn't be surprised that that's very typical SQL. right? It's a dialect of SQL. So just like any dialect of SQL, you might have some things that are not exactly the same as in other systems, but more or less the same, right? So select from where, group by, having, order by, limit of set. These are the clauses of SQL in exactly this order. This works on data frames, and it's going to automatically infer the underlying transformations and query plans. Getting back to pre-partitioning, I wanted to mention this because that's an example where I have a group by and an order by on the same key. You see, this is what I meant when it's on the same key. You group by country and you also order by country. So who sees intuitively that this requires only one shuffle, right? You just shuffle it once by interval, then you have the intervals on the machines, and then you do the group by locally and the order by locally on in every partition, right? So this is the idea in here, right? The rest, as you can imagine, doesn't require shuffling. In fact, I already explained to you a little bit. Where is basically a filter transformations, right? That's a selection. Having is also a filter transformation. Limit and offset, it's just about selecting a subset of the data frames. That's also done very efficiently, right? For example, limit can be pushed down all the way to reading from disk, right? Very often. You can really very eagerly already limit what you're reading from disk in some cases. Of course, now we have group by, order by, so you can't do it in that case because you still need to read the entire data set and shuffle. But if you don't have group by, order by, and just have select from where limit, then you can actually be efficient and save yourself from reading everything, right? By the way, there's a push down you can do here. Imagine that the data set that you're reading, persons, has 100 columns. Who sees that by looking at the query, I only need to read first name, last name, age, country, and that's it. Just these 4 columns. So you only need to read from these 4 columns, and the 96 other columns, you can just leave them on disk. You don't even need to read them, right? So that's the sort of optimizations that you can do in here with the power of data frames, right? When you read from Parquet, for example, then you can do that. With RDDs, you cannot, right? You have to read everything. Okay. So now, this is a good old SQL query that could work on a table. But I told you that data frames are a bit more generic than tables because data frames can in fact be nested, right? You remember that in data frames, we can have tables in tables in tables because the JSON objects that we validated to get the data frames might have nested arrays of objects, right? So you get the nested tables with arrays of objects. And so what happened is that people tried to extend SQL to support the nestedness of the data. Here's an example of the sort of things that they have done. They have this explode function that they put into SQL. Look at the data. It's a data frame. There's string, and here it's an array of string. I could have displayed it also in this fancy way, 1 per line and so on, right? I just squeezed it a little bit on less on the slide, but this is basically structured, right? Here it's nested structures. Well, what if you want to query these individual values? Well, you can say you select last, so this column right here, and explode countries is going to basically do this. You see, 1 on every row, and it duplicates the value in last. This is what the explode function does. For whom is this intuitive? Right? Basically, what you've done with the explode function is that you've normalized your data into the first normal form. Right? The one on top is not in the first normal form because you have nestedness, you have nested structured data. But here, you are in the first normal form. Right? So the explode function allows you to do that. But it leads, of course, to duplication because now you basically have multiple times the same value. So you can deal with SQL with nested structures. In fact, it can become quite complex because you also have a structure clause in SQL called lateral view that does the same thing. And it's especially useful when you have multiple levels of nesting. So here you have an array of objects. And inside the array of objects, you even have another array in here. So here you have multiple levels of nestedness. And basically, you can select from the table. With the lateral view, you are going to explode the values like this. And with another lateral view command, you are going to explode again on the second level, right? Who is scared by this query? You should be. Because that's exactly the price to pay. SQL was designed for tables. And now we are trying to push SQL to work on data that it was never designed for. SQL was never designed to query nested data. And so now we expand SQL to do these things, and it starts to be less and less intuitive. And now you start seeing that we're starting to arrive at the limits of what SQL is good at doing when we do that. So it's totally normal that this is a bit scary because we are arriving at the limits of what SQL was designed for. Here's another example with objects, where you have here nested objects, right? The previous one had nested arrays. Now we have nested objects. How did we extend SQL? We just added dots, right? Now you can say name dot first, name dot last, and that's how you extract the values from the objects, right? So we extend SQL with the explode function to open the arrays, and with dots to extract the values that are in nested objects, right? So this is the idea. For whom is that intuitive? Maybe this one is a bit easier, right? The dots. Of course, because that's a simple query, right? But you can imagine when the queries get more complex, how it's going to complicate the way you write your query. It's no longer Halloween, but I still want to show you a few scary things. I was assuming right now that there's a schema, in the sense that even though you're reading CSV or you're reading from a JSON lines file, there is a schema to be inferred. What if there is not? What if you have data like this that doesn't fit a schema? You see here, you have an array, and here you have integers. That happens in the real world. When you log data, the schema can evolve, and then you have data that is not completely homogeneous, right? So we've seen that technically you could validate it with a schema if you just say that's any value, right? In a schema, you can say that's any value, but then it's an abstract type, right? I said it has to be a concrete type to have a data frame. So here you can't build a data frame out of this in the sense that I have shown you before, right? So do you see that you can't build a data frame because of this, right? That breaks domain integrity. Who sees that? Just making sure. All right. The scary part is that Spark is not going to throw an error. It's going to squeeze everything into strings. It's going to take all of that here. It just serializes it into a string and creates a data frame where foo is a string and bar is a Boolean, and that's it. And basically, what should the user do with that? It's the problem of the user. So Spark has just put the burden on your shoulders, like deal with it. You know, the data is heterogeneous. Now it's your problem to deal with it. And now you can imagine the sort of code that you are going to need to write in SQL or in Python, because now in Python, you are going to try to parse this, maybe use some case, switch case, and so on to act based on the value that you have here. But you can already imagine the complexity of the Python or of the SQL code that the user is going to have to write in order to deal with this heterogeneous data, right? So Spark was kind enough to parse the document into a data frame, but the cost is that we pushed the complexity onto the shoulders of the user, right? Now there's been a bit of evolution, and I have one more scary thing to show you. It's the variant data type that actually it's existed for a while in databases or even in some programming languages. So Spark 4, it's very recent, was just a couple of months ago, they added the variant type. What is the variant type? It's a polymorphic type that basically says the values in here can be heterogeneous. They can be anything. So you could have an array, you could have an integer, and so on, right? So it's an improvement. It's an improvement in the sense that now the user no longer needs to parse the string, but the user will still need to write code, in that case with SQL, that should handle these things, right? Normally, when you write SQL, you assume that a colon has a specific type, but here you can't, right? So you will have to write some specific codes that that acts on that. Okay, who is with me on the variant? Okay, so all of that I'm showing to you, the explode function, the lateral view, the dots in SQL, squeezing things into string when it doesn't fit, using the variance type in order to force fit it into data frames. These are all the attempts to push SQL as far as we can in order to deal with denormalized data, semi-structured data, when it's heterogeneous, when it's nested, and so on. And the thing is, it actually works for simple use cases. If the data is behaving like you have just a few levels of nesting, but not too much, like 1 or 2 levels maybe, or if you have heterogeneity, but maybe just, let's say, 2 types. In here, it's still simple because you have an integer and an array. But now, imagine a data set with 10 levels of nesting and with keys that can be associated with all kinds of types, and you have a billion objects like that. Imagine the complexity of that, and imagine the SQL that you're going to have to write to query these data sets. And so I have an image that I like to give because some people tell me that kind of conveys the idea. It's as if you would have a washing machine, you know, that can do laundry, and you realize, oh, it can wash stuff. What if I try it with dishes, right? And so you basically try to fit the dishes in there. Maybe you tweak a little bit the machine so that it deals with the dishes. For example, you could make it rotate a bit less fast or that kind of things. But you see the idea, right? You've basically pushed the dishwasher to, so not the dishwasher, it's a washing machine. You've pushed the washing machine to its limits, right? And what you actually need now is a dishwasher for this. And so that's basically what we are going to deal with in the next week and the week after that. It's really this idea that data has shapes. There's data that is in the form of tables. There's data that has the form of trees, data that has the form of graphs, data that has the form of cubes, data that is unstructured, where you can use vectors now with LLMs. And so as data engineers or as data scientists, you really need to understand that once you have figured out the shape of your data, you need to use the appropriate product, the appropriate language that fits with your data. So that's what I want to convey here, right? So basically, what I'm saying is that data frames are an awesome optimization in Spark, right? So you can squeeze much more in less memory. So that's a huge optimization. It makes things faster. For data that is a bit heterogeneous, a bit nested, it also works great. You can use these features that I've shown you for if it's just pushed slightly into the heterogeneous and nested territory. But for data sets that are heavily nested, heavily heterogeneous, and very complex, then we've reached the limits of what SQL can do. Okay. So this is the end of this lecture on Spark. I can take some time for any questions that you might have. Or on Zoom. Let me still test that you're following me, because when I don't see many raised hands, I always wonder, like, is it because you're bored and I'm too fast, or is it because I completely went past you and nobody understood anything? So let me see. Exactly, just checking. Awesome, so that looks good. We have a majority here. So now the advice that I can give you is first practice, practice, practice. Now what you should do is solve the exercises, write PySpark, so use the Jupyter notebook and try to analyze data. You can solve the past exams. There's data sets in the exam docker, there's questions. Write as much code as you can in PySpark to query the data. Write as much Spark SQL as you can to query the data. That's the best way to make yourself acquainted with this, right? It is really something that you have to get practical experience with, and the TAs have designed exercises for you. The second piece of advice is to read the textbook. And the third piece of advice is to ask questions on the Moodle forum. Anything that you don't understand, any detail you want to clarify, send a question to the Moodle forum. Send an email to the TAs. Ask questions in the exercise session to your TA. Send me emails for anything that is not clear. And you can also explain to each other. So those who are in the yellow zone, for example, can explain to those who understood a bit less. All right. So very good. So that was also heavy, hopefully less complex than HBase, but still a lot to digest with Spark, right? So as a summary, Spark is the next generation MapReduce. It also uses parallel and batch processing computations. It is based on collections of anything and not necessarily key-value pairs. It's a general DAG of data flow. We see that the implementation is still done in tasks. We saw a few optimizations, including data frames that massively reduce the footprint in memory. And we see that SQL is back because you can use SQL in order to query data frames, but it reaches its limits if the data becomes too nested or too heterogeneous, because then we have collections of trees. And so we should use a query language meant for trees. All right, so I'm going to stop the recording here and move over to the next part, which is about optimization.